it's time to finish our solving of linear systems analytically. We basically said that linear systems, again, for homogeneous, second order, blah, 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 first order systems of two differential equations, blah, 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 right? We can solve this with something called eigenvalues. And we said, well, what happens if the eigenvalues are distinct and real? And then that led to the idea of straight line solutions. That was 3.2. We said, okay, if we have two eigenvalues and two eigenvectors, then there's going to be two straight line solutions if the eigenvalues are real and different. And then we said, okay, so everything along those lines is going to be a solution. We had, situations like this, where we had two different straight lines. And then we had, maybe this is a source, maybe it's a sink. Who knows? We could draw phase portraits. If it's a sink, we might have something that looks like this, blah, blah, blah. And why did eigenvectors even matter? And why did eigenvalues matter? It's because we were looking at straight line solutions, and we said everywhere along this straight line, if we're anywhere along the straight line, and again, we're dealing with the XY plane here, if you're anywhere on this line, if there is a straight line solution, then you have to be either moving directly away from or directly towards the origin. And what that translated to, this is the direction that we're moving, dy dt. That's the rate of change. And this is a vector, so it's specifically the direction of the rate of change. And so we said that direction was a times y. And to be a straight line solution, that had to be some multiple. Sorry, we said that at any vector v, right, and that could be y, any vector v that is the rate of change, that's just going to be some constant multiple of v. So maybe if we're right here, then the direction that we go is a times v needs to either be some constant multiple in that direction, same vector, or the other way. It's always really important, and I can't stress this enough. Don't get lost in the sauce here. We do all these computations over and over and over again, and we lose the meaning. Why does this equation matter? And yes, it lines up with some theoretical concept in linear algebra called eigenvalues and eigenvectors. But why did this come up with? Where did this come from in the first place? It came from looking for straight line solutions. Because if you're on a straight line solution, you have to satisfy this equation, which comes from our differential equation. So always remember that. And why did the characteristic polynomial arise? It's because we were trying to find non-trivial solutions, and we have a theorem that says we only get non-trivial solutions if the determinant of something is equal to 0. Okay, so always keep those in the back of your mind whenever you can. And that's what we talked about. And then we did some qualitative analysis. We talked about source and sinks. We said we also have this new thing called saddle points. If one of these lines is kind of like a source and one of them is kind of like a sink, then you put them together and you get some saddle point. And then we also said, okay, in 3.4, what happens if those eigenvalues are complex numbers? And that is wild, because it turns out even if they're complex numbers, we can still get real valued solutions from them, which is very, very cool. Well, if you have two distinct real eigenvalues, you're here. You have two complex eigenvalues, you're here. Well, what if things are 0, we have weird cases, but also what if they're repeated, what's going to happen? And that's what we're here to look at. Now, in these cases, if we're looking at repeated specifically, we don't spend that much time talking about 0 eigenvalues. It's mostly repeated. But if we're looking at repeated eigenvalues, both of these situations are pretty rare. Now why is that? Let's think about our characteristic polynomial. Remember, our eigenvalues are going to be found when the determinant of a minus lambda I, for reasons I just mentioned, we're looking for non-trivial solutions, is equal to 0. Now this is our characteristic polynomial. It's a function of lambda, right? We have some equation with lambdas. It's going to be quadratic for us because we're looking at two systems of two equations. a 2 by 2 system. So let's look at a quadratic. Okay. Now hypothetically, let's look at a quadratic right here. And let's say, you know, these are all lambdas. So for different values of lambda, we're looking at the determinant of a minus lambda I. Now there's a whole bunch, right? There's a whole bunch of parabolas that have no real roots, right? All of these parabolas have no real roots. The x-axis is the lambda axis. The y-axis is that determinant. We want that determinant be equal to 0. We're looking for when does this parabola cross the x-axis. There's a whole bunch of these with no real roots. And there's a whole bunch of these with 2 real roots, right? The roots are the x-intercepts, or in this case, the lambda intercepts. All right? And again, there's a whole bunch of parabolas with 2 real roots. There's very, very few parabolas that have exactly 1 real root, right? Is this reminding you of anything, by the way? Moving something up and down and wondering when it bounces off the horizontal axis? Might give you some flashbacks to when we talked about bifurcations. That's essentially why this section's useful, because it's going to arise, and we're going to talk about this more in 3.7. This sort of degenerate case, and that is what we call it when we have repeated real roots. This degenerate case really is the boundary. It's the borderline between, complex eigenvalues and, 2 real distinct eigenvalues. So this is going to be the border. If we're looking at a 1-parameter family of systems, there could be a parameter value that tips us over, going from distinct real to complex. And we're going to see that with an example. And this is very exciting. I love this stuff. So let's look at an example right now. Consider the differential equation. This is not going to be surprising. dy dt equals a times y. Wow. It's a 2 by 2 linear system, homogeneous, as we have been working on all chapter. And let's say that coefficient matrix is given as follows: -2, 1, 0, -2. Then let's look at the direction field for this. If I look at the direction field for this, again, using my nice little plotter over here, we're going to have to change things up a bit. If we plot the direction field, we plug in these coefficients, -2, 1, 0, -2, like so. We get something a bit interesting. Now it kind of looks like a spiral. It kind of looks like a spiral, but it also kind of doesn't. Now I'm going to pull something up for you real quick. I want to look at a different direction field plotter and plot the same system. This one's really good for eigenvectors, but it doesn't actually show eigenvectors correctly a lot of times when there's only one. So I want to show you a different one with this other plotter that we've also been using. I think we're going to be able to see it a little bit better. -2 times x plus 1 times y, and just -2 times y. Let's look at this. Now again, it kind of looks like a spiral. It's kind of spiraling in some sense. If you look at different startings, it's sort of spiraling. But also, we kind of do have some straight line solutions. Maybe it's like around here or something, right? So we have sort of a straight line solution, sort of a spiral. Well, that shouldn't be surprising, right? Here we have a spiral because there's no roots, no real roots to this characteristic polynomial. Here we have straight line solutions because there's 2 distinct roots. What do we have if we have repeated? We're kind of melding. One is becoming the other. which is really cool. So we have this sort of hybrid situation going on right now where we have sort of a spirally kind of behavior and sort of straight line solutions. And that's what this section is all about. Okay. So we could find our eigenvalues really quickly, right? We need to find when the determinant of a minus lambda I is equal to 0. So the determinant of a minus lambda I looks like this. And what is that? We want it equal to 0. What does it equal? Well, it's just going to be negative 2 minus lambda squared minus 0. Okay, it's already factored, right? It's just going to be when lambda is equal to negative 2. And again, this is a very special kind of matrix. This is called an upper triangular matrix. And if you have triangular matrices, your eigenvalues are always going to be on the diagonals. All right. Oh, so sorry, I should be drawing it like this, right? Your eigenvalues are always going to be on the diagonals. So it's not going to be a surprise. And again, you can see why, because look at the other term. It's always going to be 0 if one of these corners is 0. And that's true for higher dimensions as well. But anyway, we have our eigenvalue here. What's our eigenvector? Well, our eigenvector is what solves this equation. So we're going to say it's going to be negative 2x plus y equals negative 2 times v, or x. And we're going to have negative 2y equals negative 2y. Again, these should always be redundant, and you can see indeed, oh, interesting. So the second equation is redundant. This is always true. The first equation, add 2x to both sides, and we get y is equal to 0. So any vector is an eigenvector as long as y equals 0. So we can choose any such vector that we want. Let's choose the vector 1, 0. Love that vector. And again, we can see, if we go back to our straight line solutions were actually on the horizontal axis. Kind of hard to see because it doesn't really plot the directions very well on that. And then again, here it doesn't show all of them. But yeah, it's actually the horizontal axis of straight line solutions. And things are sort of spiraling elsewhere. But remember, we didn't talk too much about uniqueness for systems of equations. We didn't really have time for that. But it works pretty similar, right? If things are nice enough, you're going to have uniqueness of solutions. If we have uniqueness of solutions and it's homogeneous, they're not going to cross. Even if it's not homogeneous, they won't cross. But when time plays more of a factor, it's a little harder to see in 3 dimensions. So yeah, we have a straight line solution and things want to spiral, but they can't spiral around that straight line solution because they can't cross a straight line solution. So it's like they kind of try to spiral, then get forced into the straight line solution a little bit. And that's mostly what we have. That's this section. We also talk about 0 eigenvalues, which is kind of weird, but that's a little simpler. These repeated eigenvalues are a little bit more annoying because we found one solution, right? We found one solution. Let's use capital, right? We found one solution, right? It's just e to the lambda, right? Any constant times e to the lambda t times our eigenvector. But to get the general solution, we need to add 2 solutions together. So what do? We're going to need to find a second solution somehow. And we will do that kind of in the next video, and we'll generalize it in the 3rd video. So we are not out of the woods yet, because we can't really use what we've done so far to get a general solution. We can find one solution, but how do we find the second one? That's what we'll talk about in the next video. Welcome to this fun little hybrid section where it's kind of a complex situation with a spiral, kind of a real situation with straight line solutions. We're in the middle. We're in the border zone. And this is what happens when the real becomes complex. I don't know. That sounds like I'm trying to make a movie trailer. Bye-bye.